Hi, this is Mr. Swanson, and I'm going to be going over Notes 4.4, where we're going to talk more about polar and nonpolar molecules. If you need more information, you can reference these textbook sections at the bottom. Now, you've seen these diagrams a couple times in the last few units, but we want you to associate ionic bonds with that negative and positive ion. So we want you to think attraction between ions for ionic bond, and when we say covalent bonds, we want you to thinking about sharing those electrons. So two very different types of bonds due to the differences in electronegativity between the atoms. So here's the electronegativity chart that you will be using when you are trying to figure out how polar or how nonpolar a molecule is. So you'll use this chart, and there are different charts, so we want you to use this specific one so we're all dealing with the same electronegativity numbers. Now here is the scale that you will be given on the test to help determine what type of bond it is. And right away I want you to change the scale. And so there is no hard and fast scale that you will see where there's going to be one scale or another scale. Different sources are going to say different things. They're similar. Like we said, it's not a measured value. And so let's go between 0 and 0.3. We're going to call that nonpolar covalent. 0.31 and 1.7 polar, and above 1.7 ionic. Okay, so this is the scale, and please make those changes to your scale. The one you get on the test will already have the changes made for you. Now, another quick recap is a polar covalent bond is when you have differences in electronegativities, because one atom might have a high electronegativity, one might have a low. And so when that happens, and we'll use this example down here on the right, you can see hydrogen has a low electronegativity and chlorine has a high electronegativity. So I'll put a down and an up arrow just to say lower and higher. You're going to get these differences in charges. So chlorine is going to hold those charges a little bit more. And so we say it's partially negative, and that's the lowercase Greek symbol delta. So that's why it's getting a partially negative. And hydrogen, thus, is holding the electrons less, and it's getting a partially positive. And so there's this difference in charges. Now, it's only a slight difference, but there is a difference, and these differences can add up to make some pretty interesting properties. So Greek symbol delta, lowercase, positives and negatives, and then the overall dipole arrow with the tail showing where the positive arrow is, and it pointing to where the greater electron density is. Here's a good overview of what that looks like in a more visual sense. And keep in mind, it looks like these electrons are fixed. And that's one thing to note is these electrons are not fixed, and they're moving all over. We're talking about regions where we're most likely to find the electrons. If you think back to the couple previous units about quantum, it's not fixed. They're moving in these orbitals. And so you can see if you have two of the same atoms, that's going to make a nonpolar bond, because it's like, imagine a tug of war between you and your clone. It's going to be pretty even. But if it was a tug of war versus like me and Mr. Kuhn or Miss Ronk or Miss Doomer, I'm going to win that one because I'm stronger. So I'm going to be pulling more. So I'm more electronegative. And you see that example right here. That's like chlorine would be like the Mr. Swanson, and like the hydrogen would be like Mr. Kuhn. And then the ionic bond is when it was such a strong difference, instead of sharing, we have that electron being stolen, the chlorine is stealing it from the sodium. And so that's the ionic bond. Now, as we've been learning to try to draw the 2D and 3D shapes, we're going to start to add in what are the dipoles, where are the charges located in this three-dimensional shape. And so we can use either of these conventions, the partial positive and partial negative, or the dipole to talk about the molecule. But I think it's best if we use the partial positive and negatives to talk about just like a molecule, or like just one section of the molecule. So here there's a partial positive and negative for the OH. Here it's the same thing. Now, if you notice that this oxygen, this has like two partial negatives on it, right? Because kind of partial negative from one side and a partial negative from the other side. And so what we do then is we use the arrow from the dipole to show the overall trend in the atom. And so you kind of want to think about, like, how is it averaging out? And so, well, the oxygen's definitely getting the negative. So the arrow is here. And if we have a partial kind of on the left side and a partial on the right side, that kind of gives you this overall dipole down the middle. And so overall, that bottom side is the negative side, and the top side of that molecule is the positive side. And so when you see these molecules interacting with each other, they're going to orientate so the positives and negatives line up. So when we're using the dipole arrow, let's talk about the overall molecule. The overall molecule. Now, when you get this understanding of dipoles and partial positives and negatives, this is going to lead into the explanations for how life works. You know, why does your body work how it is? Why does the Mother Nature and the rest of the environment, why does that work? And charge separations and dipoles and polarity is a really big factor. And so this understanding of this is going to help you for biology next year. It would help you a little bit in organic chemistry as well, but we're skipping that kind of due to the nature of this online environment. But it's really important to know that organic molecules are big carbon chains, and carbon and hydrogen have such a small difference in electronegativity. A big molecule like this is pentane, is going to be considered nonpolar because it's also symmetrical. So it's got symmetry, and the difference is so small between hydrogen and carbon that those overall don't add up to polar molecules. And so you're going to get a lot of molecules that are very unlike water, which is a very polar molecule. So the interactions between these things are going to be of interest. But you're going to learn more about that in future units and next year in biology. Now, here's an important thing to note, that if you have a molecule and it's big and maybe it has some interesting shapes like this one below, if it contains carbon and hydrogen only, you know it's a nonpolar molecule. So even though there's slight differences, the overall average is essentially no differences in electronegativity when you look at the symmetry of the molecule. And so know that if it has carbon and hydrogen, it's a nonpolar molecule. Now, if we replace one of those hydrogens with maybe like an OH, suddenly this molecule has some kind of polarity, because now there's some difference in electronegativity between the oxygen and hydrogen and the carbon and oxygen. So both of those will lead to a polar side on this molecule. But for now, if we're just talking about carbons and hydrogens, know that we're talking about nonpolar molecules. So try to answer the questions. You know, are these following molecules polar or nonpolar? And then pause it, and then come back to the video in just a second. Okay, so you know this first one, you have hydrogen chlorine, and the difference, and you can think about this as absolute values. You can also just take the highest one minus 3.5 minus the lower one. It's a difference of 1.4. And again, 1.4 falls into this range, and we can change this range to be 0.31 instead. But either way, 1.4 falls into that range. So we know this one is going to be polar. Now, Cl2, you know, what's the difference between 3.5 and 3.5? And the answer is 0. And so that tells you this molecule is going to be nonpolar. And so we got our nonpolar molecule and a polar molecule. So now we're going to combine our understanding of the VSEPR theory with polarity and look at the overall molecule's polarity. And you can see that if the molecule is symmetrical, you're going to have those negative charges on both sides, and that kind of averages out to kind of no overall dipole. And so if you take a look at the example of carbon dioxide, you'd consider this a symmetrical molecule, where if you think of the dipoles as vectors, those vectors would then cancel out. So that left arrow and right arrow of the same magnitude would overall lead to a nonpolar molecule. So this is one way you could get a nonpolar molecule, because this plus this essentially equals 0. If you look at another example, and the one on the right, this one is tetrahedral with CCl4, it's also a nonpolar molecule because, again, you're adding up all of those vectors, and I'm not going to do a good job in the 3D for this one, but you can see that overall that's going to cancel each other out. And same thing with the BF3. And so look at the structure and see if it's symmetrical, and if it is, a molecule with polar bonds, like all of these are polar bonds. CCl is a polar bond, carbon and oxygen is a polar bond, B and F is a polar bond, but they cancel out. Now, we have to be really careful when we're trying to decide if a molecule is symmetrical or not, which would then cancel out the dipoles. So to do that, there's a couple characteristics or qualifications that we need to have. One is there has to be no lone pairs on the atom. It's impossible to have it symmetrical if there's a lone pair. So if we look at these examples, there's no lone pairs on this central atom. So the first one is true. The central atom has only one type on the outside. So if we look at these are all chlorines, it's also true. And in the other example, they're all fluorines. Now, one could argue that if two different atoms had the same electronegativity, that would also be true, but that's A, unlikely, and B, they're not going to be the exact same electronegativity, and so it's not going to cancel. So you want to look to make sure that there's no lone pairs around the middle, and you want to make sure those outer atoms are all of the same variety. So let's take a look at these 3 molecules that all have polar bonds, and you might be like, okay, maybe they're symmetrical. Well, let's see where they kind of break down. So number 1 is not symmetrical, and why? Let's see if you can understand why this one's not symmetrical, even though it kind of looks symmetrical. It has that lone pair. Okay, so that's why that is not symmetrical. And the second one is not symmetrical because there are more than one type of bond. Okay, and finally the other one is just a straight up dipole, so that's also not symmetrical. So actually I shouldn't have drawn the arrow there, but it's just a dipole right here. There's no canceling dipole, so that's definitely also not symmetrical. So these are all 3 polar molecules with polar bonds that symmetry doesn't cancel. So water, one of the most important molecules you'll ever study, if not the most important molecule, is that polar or nonpolar? And this is one you should definitely know. Kind of from here on out, it'll be important in a couple different units, that water being polar or not polar. And so you want to look at it. Okay, is there an overall dipole? Yeah, I see a dipole in this direction. Sorry, I drew the arrow in the wrong direction. You see a dipole kind of like this and a dipole like this. And those are not, they can't cancel out if you look at the angle. So the overall dipole for this is kind of in this direction, and maybe it's a little bit better if we draw it in another color, because I was writing in red. We kind of draw the overall dipole being like this. And so there's no cancellation. Again, it's not cancellation because there's lone pairs around that central atom. So this is definitely a polar molecule. So we want to learn this, that water is polar. Okay, so that's one thing definitely to kind of store in your mind, that water is a very polar molecule, and you can see the individual dipoles adding up to be the resulting blue dipole. So now that you've learned a little bit about overall as a molecule, is it polar or nonpolar, not just the bonds, but is the molecule polar, I want you to try to look at these 5 examples and classify them as P or maybe NP, and maybe try to show why if you can. I'll give you a hint. We omitted in these examples, and it often is, the electrons. And so you can see nitrogen's electrons are emitted here, and oxygen's electrons are emitted there. So take a look at that, pause it, and I'll have the answers when you come back. All right, so did you get these for the answers? And so I'll try to talk about why you might have decided that these are polar and non-polar. So number one is kind of following through the rule, like if it's just carbons and hydrogens, it's going to be non-polar. So that was kind of one of the rules. Number two, you can think about it, well, there's lone pairs of electrons around the central atom right here. So that's going to make it polar. Same thing down here. Again, there's differences in electronegativity, and you have a lone pair around that central atom. So here's another polar one. Number four over here is nonpolar. There's no dipole at all. There's no unequal sharing of electrons, so that's nonpolar. And finally over here, this is polar. It's got its much more highly electronegative oxygen, so the electrons are going to be it's going to have an overall dipole like that. Let me kind of draw a better arrow. So overall dipole is going to look like that. So, and here we can draw that for the arrow for these as well. Oops. Okay, so you can look at the overall which side is kind of going to be the negative and which is going to be the positive side of the molecule. So anyways, I hope this helps. Let's look at a little bit more about kind of why this matters. Now, this is one of the central dogmas of chemistry, and so now you know enough to understand this. When we say the phrase like dissolves like, it's really important that polar substances are only going to dissolve polar molecules, and nonpolar solvents are only going to dissolve nonpolar solutes. Okay, and so like dissolves like, polar dissolves polar, nonpolar dissolves nonpolar. So oil is made of just carbons and hydrogens, very nonpolar. Water, having that unequal sharing, is very polar. So that's why you don't mix those. They don't mix, okay, because they're not the same. They won't dissolve in each other. On the flip side, you have sugar. It's a very polar molecule with OH groups, so that's unequal sharing of electrons. And when you put sugar into water, it definitely dissolves because polar and polar substances dissolve. Now, this is going to help you explain cooking. This will help you explain like how laundry detergents work and why you need different stain removers because they have different polarities to remove certain stains. You can't just use water, right? Because some stains are non-polar, and so you have to use soap that has non-polar aspects of it to kind of dissolve it. So like dissolves like will be talked about in other future units as well as it's really big, important for biology.